Want to welcome all of you to our latest edition of our Sim Science class. My name is Pat Hyland. I am a research meteorologist with the Cooperative Institute for Mesospatial Meteorological Studies at the University of Oklahoma, and I work in affiliation with the National Severe Storms Laboratory. So our group is the SWAT group. We're the Severe Weather and Applications Technology Transfer Team. So our job is to kind of create tools that can help forecasters provide better forecasts and warnings to everybody in the public. So really excited to be here today. We're gonna talk about how storms get cooked up. So you can see I'm in my kitchen here. We're not actually gonna cook anything up because if you've watched Great British Baking Show before, you know that stuff takes way too long. So we're gonna talk about some of the things needed for severe weather for storms, and then we're gonna do a really cool couple of demonstrations later on. So I don't know if you guys have helped your parents at all making any sort of thing recently. I know there was a time where people were running out of, yeast and flour and those things. For storms and for all the weather that we have, we need to have a starter. A starter is really important for us. So our starter is something very interesting. I'm going to bring my presentation here, and I want you guys to give me a thumbs up if you can see that presentation. Oh, good? Okay, perfect. All right. So in order to get things started, just like you need to get stuff started with your particular bread or recipe, our weather starts with the sun. Without the sun, we wouldn't have any of this interesting weather. And the sun really does some interesting things. And there's some common misconceptions about the sun's role and what it does with our weather. So a lot of people think that the sun is actually heating up the atmosphere. And that's how, all of that, you go from warm to cool based on different parts of the atmosphere. But actually the sun is heating up the ground and the water, and then it's absorbing that heat, and then it radiates out into the atmosphere. It's typically warmer near the surface, then it gets colder as you go higher up in the atmosphere. If you guys have ever been in airplanes before, when you're at 35,000 feet above the ground, it's pretty cold out there. Even though on the airplanes, they still put the air conditioners on while you're up there. It's still cold, even outside too. So the sun's job is to heat up the earth, and the earth radiates that heat out, and that in turn warms up our atmosphere. Now you guys know that our earth is an oblate spheroid. It's a sphere, so it's kind of like a beach ball. Think about a beach ball. Now, when the sun's rays are coming in, they're not hitting that beach ball exactly the same in all different places. You guys can do an experiment with this at home. If you take a beach ball, take a flashlight, shine that flashlight directly at that beach ball, you're gonna see that it's pretty direct right in the place that you're pointing that particular flashlight. When you start moving that in either direction outside of your more direct way, there's going to be a lot less radiation in those places. You're going to notice it's kind of diffused. It doesn't look as bright. That's exactly what's happening here on Earth. So those sun's rays are coming in. They're a little bit more direct in the tropical regions. That's why it's typically pretty warm there throughout all parts of the year. But as you go closer and closer to the poles, that radiation that comes in is not as direct. And so they're not receiving as much radiation as other places. So you typically see warmer conditions in the equatorial regions and then colder conditions in the polar regions. You guys know that the Earth is made up of water and land, and most of the Earth is actually made up of water. And the water and the land heat up and cool down differently. So the land is really gonna absorb that heat really well. So it's gonna take it in really fast, but it's also gonna lose it really fast too. Whereas the water, it takes a long time for that water to absorb all of that heat, all those rays coming in, that radiation from the sun, but it holds on to that a lot longer. And so if you've ever been to a beach before and you got that white sand, you got to race to get to the water. So that's what happens, is that land is heating up really, really quickly and the water's still colder. And at nighttime, you might notice that that water seems like it's a little bit warmer than the land. It all has to do with how everything is being heated up and cooled off and how efficient it is at keeping that heat and keeping the cooling as well. So because we have this uneven heating of the Earth, we get differences in pressure throughout the Earth too. If you guys ever looked at a weather map, you might notice that there's H's and L's on it. So the H's mean those places have a lot more air molecules. There's high pressure. Have you ever felt pressure before? Like my gosh, I gotta finish this. Or you just have a lot of weight on your shoulders. There's a lot of high pressure there, a lot of air molecules. Where those L's are, where we have lower pressure, less air molecules. And the Earth is always trying to maintain some sort of semblance of equilibrium, keeping everything in balance. So what we have to do is we got to move the air from the places where we have lots of air molecules to places where there's not as many air molecules. So we got to move and get those so that everything can kind of essentially be in balance. And you know what that creates? That creates the wind. So when we get the movement, those air molecules from high pressure to low pressure, that creates the wind. And air is a really powerful thing. It can go across, west, east, go all sorts of different directions. And it's really one of the things that really gets our weather going. And remember, it all started with the sun, but the movement of air molecules from one place to another creates a wind and starts getting some of these ingredients together that we need for all the sorts of weather that we experience. Now, when you see those H's and L's, like I said, high and low pressure, this is typically what you're gonna see when you have those high and low pressure days. So when we have high pressure, you'll see that H there. There's not actually big H's on the ground, so don't worry, they're not like just floating around here somewhere. But again, remember, those air molecules are moving away from those areas of high pressure, trying to get to those areas of low pressure. So we get diverging air. And when that air sinks and diverges, it's heating up, it's warming. So typically during high pressure, we have nice sunny skies. So similar to what we have right now outside. Now, when we have low pressure, because all those air molecules are racing in from places where there's more air molecules, they converge, they start to rise, and they cool and condense, and it forms clouds, liquid water, the big storms that we get. So typically with low pressure is when we see our kind of lousy weather. That's what I'm going to talk about here. So high pressure, think of high pressure as happy weather, clear skies, calm conditions, dry weather. Enjoy these days here in Oklahoma as much as you can, because we get a lot of lousy weather around here sometimes. So when we have these days with sinking air that's warming, sunny conditions, happy weather, high pressure, that's what we typically see, and that's what we're seeing today. Whereas in low pressure, we typically see lousy weather. Now, lousy weather might be lousy for some people, and it might not be so lousy for people who are researching severe weather, but typically when we have low pressure, you get these lousy weather, you get cloudy skies, windy conditions, wet weather, and sometimes typically followed by colder weather. Now, if you've looked at a weather map before, you've probably seen some of these symbols on there. So there again, the H and the L for high pressure and low pressure. Now, because the air is moving from one place to another, it's taking air masses, colder air to places where there's warmer air, and warmer air to places where there's colder air. And again, it's all due to that uneven heating of the Earth. And so the blue line that you see on there with the triangles, that's a cold front, and the blue triangles are indicating the direction that air is going to move toward. So that colder air is going to race toward the south and the east. And then you see the red line there with the half circles on there, that's a warm front. And that warm front is, again, a boundary between the warm air and colder air, and it's going to move off to the northeast. So if you've ever looked at a weather map, or if you've been wondering how to read some of the things on the weather map, these are exactly the same things that you're going to see on that weather map. Now, these fronts are really providing a means for getting things going, and we're going to talk about those ingredients here in just a second. But what happens when a cold front comes through is, think about when you're shoveling. Basically, you take that shovel, dig it in, and lift it up. That's exactly what that cold air is doing to the warmer air in that surrounding area. So it's digging underneath there, it's forcing that air upward. We can get some really big thunderstorms that can form right on those cold fronts. That's what we typically see a lot of our bigger time weather, because again, the slope, basically how quickly that air is being forced up, is really, really impressive right there along the cold front. Whereas a warm front's a little bit more gradual. So you can still see clouds and rain and other showers along those warm fronts, but it's much more gradual. So that warm air is kind of riding up over the top of that colder air, because remember, cold air sinks, warm air rises because they're different densities. So that warm air is riding up over that cold front. And these things, and it all has to do with that air that we were talking about, movement of molecules from one place to another is getting these ingredients. So in order to get thunderstorms, you need certain ingredients. Just like if you guys ever watch Chopped with your parents, they give you the basket ingredients, you have to use those. Or if you've helped them put together something, there's a recipe. And you need to follow that recipe exactly. If you put too much or too little of something into that recipe, you know it doesn't come out exactly correct. So for basic thunderstorms, these are some of the ingredients that we need. And again, if we don't have all these things in place, we won't see those thunderstorms. So moisture is a really big ingredient that we need. We're very close to the Gulf of Mexico, so that warm, moist air is racing up here. So that can provide some moisture for us. A lifting mechanism. Remember, the air moving from one place to another, and you get the boundary between different types of air. You have those fronts, like the warm front and the cold front. That can help lift that air from the surface, and then it cools and condenses and forms clouds and liquid water. So that's really important. We need something to lift that air up. Now here in the Southern Plains, we have something called the dry line. It's the boundary between the dry air to our west and southwest, the more moist air to our east. And that dry air starts to mix out. Some of that warm air starts to move a little bit to the east, and then it retreats back at night. And so that can be another source of lift. That's why we tend to see some more thunderstorms around here, is because we have another source of lift that you typically don't find in other parts of the world. And then we need the atmosphere to be unstable. And what I mean by instability that you see here on the slide is that on days when we have an unstable atmosphere, air can just freely rise. There's nothing really stopping it from rising and forming these big giant clouds, these cumulonimbus clouds you may have heard of before. So on those days, those air parcels can freely rise. Nothing is stopping them. Think of a hot air balloon. When they pull on that little lever, they release the heat up into that hot air balloon. That hot air balloon is going to continue to rise. And it's going to keep going as long as it's warmer than its surroundings. And so on days when we have really big, severe weather, we have a really unstable atmosphere, and those air parcels can just freely rise. So I've got a time lapse here showing you how thunderstorms typically form. When you put all these ingredients together, you can see just how explosive the growth can be of these thunderstorms. Look at that. Do you see how quickly those clouds are going up there? And then I know you guys live here in Oklahoma. You've seen a lot of these things before. It gets that characteristic anvil shape. Do you see it kind of looks like an anvil? If you've ever watched like Wile E. Coyote before and the Roadrunner dropping the anvils everywhere, that's exactly what that looks like. And you can see the different stages of these thunderstorms as well, which is really cool. Thunderstorms typically start off with air that's just moving up. So air can move upward. It's called the updraft. As it gets more mature, when you get into that stage where it looks like it has the anvil there, you have an updraft, so you have air going up, and you have a downdraft. You have air coming down. That's because all that rain and hail, all of it is a lot colder and cooler than its surroundings, so it falls and spreads out. And then you could see the dissipating stages of it too later on, when the newer stuff is growing off to the right side of your screen and the stuff on the left is kind of fading away. So you can see all of the different ways that the thunderstorms form and mature over that time. So here in the United States, this is typically what we see. We live in a very unique area. 80% of the world's tornadoes occur within essentially that red area that you see there. Now, I'm not saying any of this to scare anybody by any means. We've got some of the best people working on forecasting and warning severe weather at the National Weather Center. You guys know that. So we're always prepared for all that stuff and letting all of you guys know exactly what's happening in those areas. But you can see, look at this map. It's all the movement of air from one place to another. So it's the cold, dry air coming down from Canada. It can make it all the way down to the Yucatan, into Mexico sometimes if it's cold enough. That warm, moist air coming up from the Gulf of Mexico, that drier air coming from the desert Southwest, where you get the intersection of those different air masses. You can see those fronts on there. And then those other ingredients I was talking about. So an unstable atmosphere, moisture, lift, all of this is here. There's another special ingredient, it's called shear. Shear is the change of wind speed and wind direction with height. And that can get some things turning too. So picture the winds really high up in the atmosphere moving this way. And then at the surface, they're moving this way. So when they start moving different directions, different speeds, that's what gets things to start spinning. So when you put all this stuff together, you can get these storms. So thunderstorms, and it's all, again, this is all the movement of air. We're going to talk about air here in a second. The movement of all of this air can create things like tornadoes, which you guys are familiar with. And then those thunderstorms can have other hazards with them too. They can create things like lightning. Lightning is 5 times hotter than the surface of the sun. That's why you don't want to mess with it whatsoever. You want to be inside. We're going to talk about some safety stuff at the end of the presentation here. But there are lightning strikes happening all over the world all the time. It's because of these thunderstorms. And again, it's the movement of air from one place to another. The Earth is trying to keep itself in equilibrium. Other hazards, we're seeing a lot of this right now up in Michigan right now, flooding. So people take moving water for granted, but if you have storms that form and they don't move anywhere over a certain period of time very quickly, you can get flooding conditions. You can also get flooding from maybe snowfall or rainfall in mountainous areas going into more valley areas. And then in Michigan, like we're seeing, you know, you have flooding because there's a lot of rainwater, and then dams can break too. So all of these hazards come from thunderstorms. There's also hail. We've seen a lot of this in the 2020 severe weather season. We've seen a lot of wind and a lot of hail. And hail can get up to the size of tennis balls, baseballs, softballs. The largest piece of hail that we've actually measured was 8 inches in diameter, and that was in South Dakota. That's basically a size 3 soccer ball falling from the sky. Think about how strong that air has to be to hold that up inside the clouds to be able to grow. We're going to talk about the hail cycle as part of our little demo also. Okay, so I've done all of the introductory stuff. So we gave you the starter, that was the sun, the sun's role in creating all of those ingredients, and then the different ingredients that go into creating all of our storms. So now what we're going to do is move on to our demonstration portion. So I hope all of you have all of your materials with you. Looks like, let me see, got about 15 people on here. If you want to show your screen, you could totally do that. If you don't want to, that's perfectly fine. You could do this demo at another time. So feel free to do that. So we are going to simulate air moving from one place to another and creating thunderstorms. So this is our source of air here. This is our hair dryer. So I've done this demo so many times, like I've used it, like I've just run out of hair, so I've got nothing left. But hopefully you guys, if you want to grab your hair dryer, I've got a little bit of movement here, so I could show you all this really easily. So what we're going to do is, when I turn on this hair dryer, what direction is the wind going to go? You guys know? Well, is it going to go up? Is it going to go down? Is it going to go left, right, this way? Air is invisible. You can't see it. So I could turn it on. How do you know where the air is and how it's moving? So the air is made out of nitrogen, oxygen, and water vapor. Can you see nitrogen? Can you see oxygen? Can you see water vapor? You can't see any of those. Now you might be saying, well, wait a minute. Water vapor, I could see that when it's really cold outside, when I breathe out. Like, what's that little thing for? Well, so you're exhaling water vapor, and it cools and condenses and forms that cloud that you see. So that's liquid water. That's not actually water vapor. You're exhaling that. So you can't see nitrogen, you can't see oxygen, you can't see water vapor. So it's all invisible. Air is invisible. So how are we going to know that it's going from one place to another? So what we can do, though, is let's pretend that this is a cloud. So I'll turn on my hairdryer now. And you can make that a little stronger. Now, the interesting thing is it takes about there's about a ton of water in one tiny puffy cumulus cloud. So think about how much air has to be forced upward to keep that cloud from falling on top of all of us. So that's showing you again how powerful air can be, keeping those clouds up there. And think about when you have those big cumulonimbus clouds up there, how much air is actually being forced upward. So my next question is, you could see that. So I hope you guys are trying this out at home. It's really cool. So look, it's just like floating there. And I'll bring it a little bit closer so you can see it. Now tell me something. If I tilt this hair dryer, well, actually, before we do that, if I move the hair dryer left and right with that ball suspended on it, is the ball going to fall down, or is it going to follow the hair dryer that whole time? Let's find out. Let's move it. See, it's not falling because that air is keeping that cloud, our little ping pong ball, suspended up in the air. It's not moving. It's moving along with it. Now, if I tilt this hair dryer, if I start tilting it like this, what do you think is going to happen? Is the ball going to fall down, or is the ball going to stay in that same place? Now let's see. So you can see it basically goes, it can tilt up to a certain point, but then it falls down to the ground. Have you ever been outside before and it seems like it's sunny right above you, but then you're starting to feel raindrops? So it's raining even though it's sunny outside. Thunderstorms can be tilted. So the thunderstorms can be tilted. You can actually be impacted by a storm that could be really, really far away. And so thunderstorms can be tilted. So that's a really good example of how thunderstorms can be tilted. I was able to tilt the hairdryer, and you're still able to suspend that ping pong ball there, even though you think it's really far away from where that air is actually traveling. Pretty cool, huh? Up to a certain point, like I said before, it starts to fall. All right, so that is how you can get thunderstorms to form, how thunderstorms can also be tilted too. Now, I talked to you about the different stages of thunderstorms. Now, the different stages of thunderstorms in that kind of formative stage, right, when it's starting to begin, we have just an updraft. So we have air that's just going upward. When we get to that more mature stage, that's when we start to have air moving up and down, get that downdraft. So what we're gonna do is, if you wanna take your paper towel roll or your toilet paper roll, I've done this demo so many times, I have PVC piping for all of this, so you can actually use that too. So we are going to simulate that updraft in that thunderstorm just to show you how powerful air can be and how fast it can move. All right, so what I want you to do is, with your hairdryer, you're gonna make sure you can suspend your ping pong ball, and then what you're gonna do is you're gonna take your toilet paper or paper towel roll and put it over the top of the ball and see what happens. You see how that got shot up into the air? That's what happens when you have an updraft. You confine that air into a really small space and then it shoots upward. That's what happens. That's why thunderstorms can keep large pieces of hail up there. It's because you're confining that air into a really, really small space, and that can get those big pieces of hail to form. And when you have updrafts that rotate, that can give you tornadoes. The updrafts that rotate, those are called mesocyclones. If you've ever watched the broadcast meteorologists on TV here in the Oklahoma City metro area, you've probably heard them say mesocyclones so many times there's a bingo card, I think, that's out there that you can actually check that off on. So now that's an updraft for a regular thunderstorm, but you guys know here in Oklahoma, we don't have regular thunderstorms. Our thunderstorms usually have really big updrafts. So now take your paper towel roll, do the same thing. So put the ping pong ball over the hairdryer and then put your paper towel roll over that and then see what happens. That one hit my ceiling. You see how high that went up? So the bigger that updraft is, the more intense that air is going to be moved upward in that small confined area. So that's exactly what happens when we have those really big thunderstorms here in Oklahoma. We have really big rotating updrafts like that. I'm seeing a lot of you doing the demo. That's awesome. That was really, isn't that cool? Now you can actually, if you direct your hairdryer in just the right way too, you can like fire it across the room or people that are sitting in other areas. That's exactly what's happening inside thunderstorms. Now what's really cool with this demo we can also do too is we can kind of talk about the hail cycle with this too. So hail forms when we have water droplets that are at the lower parts of the cloud where it's warmer, and then that updraft picks up those water particles and they go to parts of the clouds that are colder. Thunderstorms can sometimes go to the very top of the troposphere and even sometimes into the stratosphere. So they could be 50, 60,000 feet. It's up there, it's really, really cold. So when it gets up to those colder areas, it freezes, and then when gravity carries that down to the ground, or it might get outside of that updraft area, it falls, and then it starts to melt a little bit. The updraft may pick it back up again, and then it starts to freeze, and this whole cycle starts over again. So you can kind of simulate that with your hairdryer. I've got a special button on mine that has a little cool feature. So what you can do is, so pretend this is at the lower part of the cloud where it's a little bit warmer, and then it gets moved up by the updraft to the colder part, and then it kind of bounces up and down as it's being carried up by that updraft and going in different parts. So you can hit that button back and forth and make it look like it's bouncing back and forth through those different parts of the cloud. So that's exactly what happens in thunderstorms. So again, this is all the movement of air from one place to another, and air can move all sorts of different directions. It is invisible. So the way that we're able to see all of this stuff, it manifests itself in the clouds and the thunderstorms that we see on a day-to-day basis. So to talk about air a little bit more, we're gonna do another cool demo. If you guys were able to eat ice cream in the last several days or so at Sonic, now's the time we're gonna create like a little air cannon. We're gonna do a little vortex cannon. So we're gonna go ahead and do that demo now. So make sure you get out your materials. So what we're gonna need is your Sonic Cup, official Sonic Cup. That's one that really works really well. And I hope you kept that dome. This is really important. So we need to have this, very important. It's gonna help direct our air going to certain places. So what we're gonna do, and if you wanna get your parents to help you out with this too, is we are going to be utilizing some scissors. So what we're gonna do is in this Sonic Cup, we're gonna cut out the bottom here. So I'm gonna take my scissors, just do a little hole there. And you guys can do this along with me too. I have one already made, so you'll be able to see the finished product here. So just cut out a little slit there, and then you can use your finger to take out the bottom portion of it. Isn't this awesome? You get to like eat ice cream and then make science out of it. Like, I just think that's the best day ever. So, and like I have 2 of them, so I actually ate like 2 ice creams in order to get this. So now what we're gonna do, so go ahead and put that dome on top. So you can see now I've got the dome secured on the top here, and I've got that hole there on the bottom. Okay, so now's the really important part where we're going to create the ways to move our air from inside here quickly out of this area right here. So go ahead and take your balloon. You gotta stretch it out just a little bit. And we will make sure to give you guys all these instructions if you wanna do this at home also. So what we're gonna do is we're gonna blow up the balloon just a little bit. You can make noises with it too if you want to annoy some people in your house. So I'm just giving you a whole bunch of stuff to annoy people in your house with while you're locked up with them. So, all right, so what we're gonna do now is just inflate it just a little bit. And then go ahead and tie that knot in the balloon at the bottom. And you'll see why we're doing this here in just a little bit. So we're gonna tie that knot just like that. So what we're gonna do is we want this here because we want this to force that air through. So what we're gonna do is we're just gonna deflate the balloon a little bit here at the top. So just a very small pop right there. And then make sure you even out the top part of that balloon there. So I cut that out. And then what you're gonna do is you're gonna stretch this out over the bottom of your balloon. Excuse me, you're gonna stretch this out the bottom of your cup. So stretch this out. I already have a couple of made here. So what we're gonna do is stretch this over the bottom of the cup. This is what's gonna force all of that air out of our little air cannon. Then what you're gonna do is you're gonna use that rubber band in order to hold that balloon in place. You may have to inflate and deflate that balloon a couple of times just to make sure that you've got enough to work with. So see what I did there? Got it on the bottom. And again, this is what you're gonna use to force that air through. So then you can put the rubber band over. This just helps secure the balloon on there. If you have a big enough balloon, you may actually already have it covered the whole cup pretty well and not have to use this little rubber band to secure anything, but just provides a little bit of extra to work with. So how's everybody doing out there? Do you guys have your air cannons made? So look, I've got my air cannon now, it's made. I have an extra one too, just in case. So then what you can do is feel that you can either do it to yourself, you can do it to your siblings, you can do it to your parents. Pull this back, fire it, you actually will be able to feel the air coming out of there. And what's really cool is if you have a little fog machine, you create a little fog inside these two. If you pull this and let it go, you'll see a little vortex ring that'll come out of this air cannon. And the reason for that is because the air here in the center is going out a lot faster than the air here on the edges. And so it creates this little vortex. And it's that air that's accelerating out of this area. So it kind of simulates what happens when tornadoes form, is that air is being accelerated and it's not traveling at the same speed all across the same area. So did you guys flinch when I did that? So I think I saw a couple of eyes that flinch when they did that. So yeah, you can actually make your own air cannon now. So again, we'll provide all of these materials for you guys if you want to do this after this presentation also. So we'll make sure that you guys get that. But like I said, the really cool thing about this is you can eat a whole bunch of ice cream at Sonic and be able to do this. Now this is a small, so if you get a medium or a large, then you can get a lot more air going through there. So all you need is a balloon, rubber band, and then your cup from Sonic, and you can create your own air cannon, your own little vortex cannon. So this just shows you how powerful air can be. If you want to do a big version of that, a really cool giant version of that, you can use a trash can. So what you do is for the lid, take the lid off of that plastic trash can, put a shower curtain over it, and then use bungee cords to hold it in place around that opening. And then on the bottom part of the garbage can, cut a small hole in that circular area that you see at the bottom of the trash can. And then if you've got a fog machine, you can actually put fog in there, and then you can hit the back of that trash can where the lid is, where you got the shower curtain, and it'll actually fire out those vortex too. We've done that at Frontier City's Science Days. It was really, really fun. So if you guys want to do a big version of that, it's really cool. You can see the vortex rings going for really far, really, really far. If you want to do a bigger version of this too, that I've also done, you can take a beach ball and a leaf blower. If you have a leaf blower, you can actually do this outside with a beach ball, and you'll see, you can put the beach ball right over the leaf blower and it'll be suspended in the air right above there, and you can move it, you can tilt it, you could do all of that. So if you need a reason to get outside and do some other experiments, those are cool ways to amplify these two experiments that I showed you here. So all fun and games, yes, but I want to make sure that you guys are safe and that you know about, I know you guys are familiar with these severe weather hazards, but I want to make sure that you guys are safe, especially this time of year when we're expecting a lot of severe weather. So what I'm going to do now is we're going to go back to our presentation. I'm going to show you guys a little bit of weather safety stuff so that you guys are ready. The next several days are going to be very active for us for severe weather. So now is the time to start getting ready for that stuff instead of when it's too late. So tornadoes. Definitely do not want to be outside if there's any threat for tornadoes. I know it might be cool to go outside and look at them, but save that to the people that are doing the research and trying to figure out how these things move, and then giving you guys different warnings on all this stuff. So leave that to the professionals. Stay at home. If you happen to be in a rural area where you don't really have a good shelter there, this is where you want to plan ahead. You want to be proactive. You want to do the stuff well ahead of time, not when the warning is issued, because that's too late. You want to do that maybe a day in advance. Get to a safer spot. If you happen to be caught outside in your car, do not hide in that car. Don't go underneath overpasses. You want to get to a low-lying ditch. You want to be away from all of those strong winds and debris. So make sure that you're away from all that stuff. Outside is definitely not the place to be. Don't want to be outside. You should plan to not be outside when there's severe weather. You want to stay inside. Inside is by far the best place to be. Strong, sturdy structure with as many walls between you and the outside as possible. If you live in an apartment complex, make friends with your first floor neighbors. So you want to make friends. You got to make friends. Even during this time when we're sheltering in place, it's really important that you guys are safe and sheltering. We want to make sure that you're safe and sheltering for all these things as well. So lowest spot away from windows. So your safe spot in your house, a lot of people sometimes automatically go to a bathroom, but what if your bathroom has a skylight? It's not a good place to be, because if that skylight breaks, debris and other things can get in there. So you want to identify that place and start identifying that stuff now so you know exactly where to go. If you have an above ground shelter or below ground shelter, those are really good places to hide too, because those are built specifically for all of that stuff. In terms of lightning, we tell people when thunder roars, go indoors, or when you see a flash, dash inside. So really one important things that you want to know. Don't want to mess with lightning. Like I said, it's 5 times hotter than the surface of the sun, so you don't want to mess with it. Avoid being the tallest object around. Don't be near water. Your car can actually provide you with some protection. Your car is a protective electrical cage. It's called a Faraday cage. As long as you don't touch any of the metal objects inside your car there, you are completely safe inside your car. And it's not because of those rubber tires. Those rubber tires actually explode if your car gets struck by lightning. Those hubcaps travel like 100 yards away, but you'll be safe inside your car. So if you can't find a sheltered space that's a good structure with wiring that'll carry that current to the ground, you want to make sure that you're in your car. Definitely not outside. Don't hide underneath pavilions at parks or anything like that. And while you're inside, make sure you stay away from any sort of appliances or plumbing. You can use your cell phones and your tablets as long as they're not plugged into the wall. So if they're plugged into the wall, current can travel through there. So make sure that if you are using those, make sure that they're not plugged in. When we have severe weather, you want to make sure those things are charged as well, so that you guys have the ability to still get information and look up information afterward. Don't mess with water whatsoever. It only takes 6 inches of moving water to knock you off your feet. It only takes about a foot of water, moving water, to move a car, and about 2 feet of moving water and less to get a big SUV going. So turn around, don't drown. Stay away from those flooded areas. Be patient, wait for it to go around. If you happen to be in a low-lying area or flood-prone area, make sure that you seek higher ground. It's especially important. A lot of people take flooding for granted. They think that, you know, it's just moving water. How's it going to harm them? But flooding actually causes more casualties here in the US than tornadoes and hurricanes on an annual basis. So it's really important to remember. And I know I'm preaching to the choir because you guys are all smart. You guys know all of these safety tips and everything you need to do. We've seen a lot of hail, a lot of baseball hail, a lot of big hail this severe weather season. Head inside. Again, if there's any severe weather, regardless of any of these hazards, stay inside. That's the best place to be. If you have time to close your blinds, drapes, and things like that, you can do that. That actually might help with keeping some of those hail pieces outside, but don't make that a priority. Your priority is to get sheltered and safe. So if you have time, you can do that. If not, go to your sheltered space. And if you happen to be driving, don't hide underneath those overpasses, because if you have a whole bunch of people hiding underneath those overpasses, you're going to be blocking other emergency personnel or others that are trying to get through there. So your parents have insurance on your cars. So you want to make sure that you don't block those areas. Your car can be replaced. So we want to make sure that we're allowing those people to go through. So don't hide underneath overpasses for any of those things. I'm going to leave this up here. If you guys have any questions, now is the part of the presentation. We've got a few minutes left. So I'm happy to take any questions that you guys have on the presentation today. You can write those in the chat, or if you want to unmute your microphone, you can also ask me a question. And it can either be about the things that we presented. If you have any questions about what it takes to be a meteorologist, some of the things that meteorologists do and the different careers, you can also ask those questions too. And any sort of weather question that you guys have, I'd be happy to take those. So do we have any questions from anybody? Anybody? See, I told you, you guys are too smart. You guys know everything already. So let me see. I want to see your guys' cameras. I want to see, did you make your air cannons? Did you guys make your air cannons? Or let me see your hair dryers. Do you guys have your hair dryers with you? Like I said, the only reason I have a hair dryer now is for these demonstrations. I can't use it on mine. My hair dries the instant that I get out of the tub or the shower. So, okay, perfect, good. You got your hair dryers. Now you guys can show your classmates and your friends those demonstrations and talk to them about thunderstorms. And you can talk to them about how hail forms too. That's great. So now I want to see, yeah, I want to see you guys with your hair dryers and show me the ping pong ball on top of there. I want to see those. Let's see if you guys have mastered this. Oh, look at that. That's awesome. The three of you have it down for sure. And I see the lamies over there with their ping pong ball and hair dryer. That's awesome. And now, okay, yeah. So look, everybody look at Taya's screen. So yeah, you can use that balloon too. That's perfect. So, and that's a really good illustration of when the atmosphere is really unstable. So again, think of that balloon. That thing just shoots right up into the air when it gets into that updraft. So that's really good. That's smart. That's really smart. So does anybody, let's see, did anybody make the sonic air cannon? Did anybody do that? Don't worry if you didn't, because that just means that you get to go to Sonic and you get to do that later on. Okay, perfect. All right, I don't see any questions from anybody. I know we have Greg and Tanya on here. If you guys have any last minute remarks about this, otherwise, I know I'm the only thing standing between a lot of these folks and lunch, so I don't want to take up too much of their time.
Thank you so much, Pat. You did an awesome job, and it was very informative. So be on the lookout for our next email in the next coming weeks so that we can do another fun, exciting class. And if you guys have any questions, feel free to send us an email. Pat had his contact information in the email, or you can forward it back to me, and we'll make sure that you get your questions answered, okay?
All right. Yeah, Greg, did you have anything?
I just wanted to thank everybody for joining again. I'd like to thank Pat for an absolutely excellent talk and demonstration. And as Tanya said, keep your eyes open. We're going to be on this. I know summer camps might not be going on yet, and they might be delayed this summer. So we're going to try and have some more fun activities for you this summer. So just pay attention to your emails, and hopefully we'll have some more opportunities.
All right. Well, thank you all so much for joining us for this Sim Science class, this Cooking Up a Storm edition. Hope you guys are all being well and staying safe and making all your good decisions. Make sure you guys wash your hands and make sure that you guys are being safe and making good decisions. We'll see all of you next time. And I know it's basically summer break, so enjoy some of that time off. You got a little bit of time off. All right, everybody. We'll see you later. Have a great day.